Lesson 5.1 Kepler's Laws of Planetary Motion. After studying motion of the planets, Kepler came up with his laws of planetary motion. So what happened is Kepler had a mentor named Tycho Brahe, and Brahe went through and plotted the positions of all the planets over a long period of time. Kepler used all that data to come up with the pattern that the planets made and to come up with equations to model them. Newton then proved them all using his universal law of gravitation. So our assumptions. We have a small mass m that orbits a much larger mass, capital M. So we can use capital M as an approximate inertial reference frame. Also, we're assuming the system is isolated. Kepler's first law is that the orbit of each planet around the Sun is an ellipse, with the Sun at one focus. The closest point to the Sun is called the perihelion. The farthest point from the Sun is called the aphelion. Kepler's second law is that each planet moves so that the imaginary line drawn from the Sun to the planet sweeps out equal areas in equal times. So you can see on the picture here, in order for area A1, A2, and A3 to all be the same, we're going to have to go fastest when the planet is near the Sun and slowest when the planet is far from the Sun. So as it gets near the Sun, the planet speeds up. As it gets further away from the Sun, the planet slows down. And Kepler's third law, the ratio of the squares of the periods, that's the time it takes to go all around in one orbit, of any two planets about the Sun is equal to the ratio of the cubes of the average distances from the suns. In other words, t squared over t squared, so that's our period, the time it takes to go around once, equals the radius cubed over the radius cubed. Let's talk about the parts of an ellipse, since the planets orbit in ellipses. A is the semi-major axis, or the distance from the center to the vertex, which you can see in the picture. A is the distance to the aphelion plus the distance to the perihelion. So we have RA from the focus to the vertex, the furthest away, and RP, the focus to the closest vertex. B is the semi-minor axis, which is the distance from the center to the co-vertex, which you can see there. And it turns out to be the geometric mean of the RA and the RP, the distance to the aphelion and the distance to the perihelion. C is the focal length. That's the distance from the center to the focus. On the diagram, you can see that C plus A equals the RA. So C would be RA minus A. The area of an ellipse is pi AB. And the measure of the ovalness of an ellipse is eccentricity. It's how stretched out the ellipse is. Eccentricity is C over A. If the eccentricity is 0, you get a circle. The eccentricity is 1, it's a line, and you can only get values between 0 and 1 for ellipses, for our eccentricity. Most planets orbit nearly circular orbits, so their eccentricities of the planet's orbits are near zero. Let's say the perihelion of the moon from the Earth is 358,000 kilometers. Its aphelion is 399,000 kilometers. What is the moon's orbit, semi-major axis, semi-minor axis, focal length, and eccentricity? Wow. So the perihelion, that would be the RP, and the aphelion that would be RA. Okay, so let's start with the semi-major axis, A. A is RA plus RP over 2. So that's 399,000 kilometers plus 358,000 kilometers divided by 2 gives us 378,500 kilometers. What is the semi-minor axis? B. B is the square root of RA, RP. Okay. So 39000. That is 377,944 kilometers about. We'd round, of course. The focal length, C, is the RA minus A. So RA was 399,000 and A was 378,500. Which would be 20500 kilometers. And then the eccentricity. The eccentricity is C divided by A. So take those numbers we've calculated and divide them. Make sure they do have the same units. And I get 0.054, which is not very eccentric, is almost zero. So it's a very circular type orbit. If it takes 27.3 days for the moon to orbit the Earth, how much area does a line from the Earth to the moon sweep out every day? So maybe we could just take our area and divide by the time. Our area is pi AB. All right, so our A from our last problem was we're going to change it to meters now, 3.78 times 10 to the 8 meters. Let's just take our kilometers and times by 1,000. B was 3.779 times 10 to the 8 meters. So that's what we had on the last problem, times 1,000, because the last problem we had it in kilometers. And we'll divide by our time, which is 27.3 days. Now I left it as days because I want how much it sweeps out every day. So when I divide those, multiply and divide, I get 1.65 times 10 to the 16 meters squared every day. So it's a lot of area. The moon's average radius of orbit is 384,399 kilometers and takes 27.322 days to orbit the Earth. The International Space Station's average radius of orbit is 417.5 kilometers above the Earth. What is the period of the ISS's orbit? Well, I think here we're going to use Kepler's third law. That's the one that's t squared over t squared equals r cubed over r cubed. All right, so we would pick one of them. Let's say this top is the moon, and then the bottom could be the ISS or something like that. For the moon, my time is 27.322 days. And we're looking for the ISS. The radius of orbit of the moon is 399 kilometers. That's cubed. For the ISS, it's 417 kilometers. But that's above the Earth. So our radius for the ISS is going to be 417.5 kilometers plus the radius of the Earth, because it's there. But we also have to add the radius of the Earth, which if we look up our references is 6380 kilometers. So our radius of orbit for the ISS is about 6797.5 kilometers. All right, cross multiply. And I'm not going to multiply or cube, square these things yet because they're such big numbers after we do that. And then divide. So it'll be whatever this is. Don't forget the squareds and the cubes divided by the 399 kilometers cubed. And I put that in the calculator and I get 0.0041279 days squared. So I square root that. Let's put it over this way. So our period is 0.0642 days. There's 24 hours in a day, so multiply by 24 hours per day, and we end up with 1.54 hours for the orbit of the International Space Station. So every 1.5 hours, it's gone around the Earth once.